constant, it takes the same value here. It's balanced, it takes different values here. And I think what's going on is clearer when you draw the truth table of the different values this function f can take. So you could have it that both f of 0 and f of 1 give 0. You could have f of 0 is 0 and f of 1 is 1. Other way around. Or you could have them both being 1. OK, so which are the even functions and the odd functions here of these lines? Yeah, correct. That's even. And these two are odd. An equivalent way of stating this task is that you want to bitwise add f of 0 and f of 1. So this is equivalent to Are people familiar with bitwise addition? Cool. So what's the bitwise addition of f of 0 and f of 1 in this case? I guess that's the easiest one. 0. Next one? The next one's not 0.
1.
Yeah. This one's 1. Perfect, yeah. So if you get that their bitwise addition is 0, you know that they're even. If you get that their bitwise addition is 1, you know that they're odd. Cool. Now, classically, if you wanted to determine whether this function was even or odd, you'd need to calculate f of 0 and then calculate f of 1. So it takes 2 calls to the function. What I'm going to show is that with Deutsch's algorithm, you can actually get away with just 1 call. Okay, and the way in which you do it is you appeal to this idea of an oracle. And this idea of an oracle is rather abstract at first, so let me spend a while trying to go through it. So in essence, your oracle evaluates f of x. But you can't just have a sort of simple box where you feed in some input and it computes the output, because this wouldn't be reversible. And as Lisa said yesterday, quantum computing got to be reversible. It's made up of unitary operations which are reversible. And the way you can see that it's not reversible is, suppose you're dealing with this function here. So it's going to take 0 to 0, and then also takes 1 to 0. So if you're looking at an output 0, and you want to try and invert things, you don't know whether to go back to 0 or 1. It's not reversible. You essentially lose all information about the input. I don't think the red one works. No. Okay, so instead, what you use is an oracle of the form up there. And now this is reversible because you maintain information about the input. Okay, so for simplicity, I'm just going to suppose that the input state here, the Q here, is just 0. And then let's look at how it behaves. I'll just write it up again, actually. If we say this is 0, it gets simpler. Actually, no, I'm not going to say that figure right yet. Okay, so what does it do? The 0, 0 state, what does that tend to?
0
Well, not quite. It depends what f of 0 is. So it's going to be 0, f of 0. Okay, so now 1, 0.
1 plus f of 0.
No.
1 f of 0.
Yeah, no. 1 f of 1.
Yes.
1 f of 1.
F of x.
Yeah, and the x is 1 in this case. No, it's not. If you had f of 0 again, it wouldn't be reversible. Yeah. Okay, and we're working with a binary function here. F of 0 can only be 0 or 1. Exactly. I'm just going to use an overline to denote that. So just sort of, I guess, a little corner up here. If f of 0 equals 0, f bar of 0 equals 1, if f of 1, f of 1. So this overline just denotes that you're doing the not. It's the opposite. Okay, final one. What does that go to?
1 and 1 plus f of 1. So 1 and f not 1.
Correct. Cool, okay. So that's how the oracle works, when you just feed in a single input each time. It gets much more interesting once you allow yourself to feed in superpositions. Okay. Any guesses on what this goes to? Ideally from someone who's not studied Deutsch's algorithm before. So you're trying to combine this with what we've drawn over there, effectively. So we know the action of the oracle on single inputs. And the question is, what happens now when you feed in a superposition? Take a guess.
Superposition of the...
Correct. So as 0, 0 goes to 0, f0, that's going to be the first one. And 1, 0 is just going to be 1, f of 1. And we know this has to happen because quantum mechanics is linear.
One question. What you're saying there is that you've got one input is the plus state and the other state is the zero.
Correct.
Okay, because I've got mixed up. And then in the top corner, what's the difference between the first line and the third line? F of x and f of x are both equal. One is equal to 0, one is equal to 1.
I'm just trying to show what this overline notation means. Maybe it's too small to see it. Let me do it in color. Okay.
So the first and the third line, what's the difference? And the second and the fourth.
So the idea is if f of x equals 0, then f bar of x is going to be 1. So it just takes the opposite value. And if f of x is equal to 1, then the opposite is going to be 0. And in answer to your first question, yeah, what I've done is I'm now putting that as a plus and that as 0. And I'm looking at what's the output. Cool. And so what we have here is we have, in some sense, in a single call to the oracle, evaluated both f of 0 and f of 1. And this is what is known as quantum parallelism. Okay, but if you were to measure this state, and actually it doesn't matter which state you measure, whether you measure the first qubit or the second qubit or both qubits, you're either going to get the state 0 f of 0 with probability 1 over root 2 squared, so probability a half, or you're going to get 1 f of 1 with probability a half. So you're only going to get a single outcome. So if you just measure it as it is, it's not very useful. You're back to the classical situation. You'd need to run it multiple times in order to get the different values. Okay. So if you want to get any useful information out, well, not useful, if you want to try and solve the task that we had at the start and try and do it more efficiently than classically, you're going to have to do something more clever than just measure it straight away. And the idea is to use interference. And this is effectively what is done with the Deutsche algorithm. Okay, so I've stated the Deutsche algorithm up there. When you first stare at it, it's not really clear what it does. But the first thing, in order to evaluate how it acts, the first thing I want you to see is we can write the action of the oracle we can write the action of the oracle like this. Wait, actually, that's not true. X. And let me just spell you through how you get this out, because it's not obvious at first. So let's start by looking at the action of, so suppose x is 0. So what I'm doing now is I'm supposing that, suppose that's 0, and that is minus. Okay, someone who's new to quantum computing, not done Deutsche Algebra before, what does this expand as?
What's the question?
How do you expand this state? How do you write it?
0, 0 minus 0, 1 over square 2.
Correct, yeah. Cool. Okay, and now what happens when we apply the oracle? Same argument as before, using the linearity of quantum mechanics and the action on the individual inputs.
0 minus 0 f dash 0.
Correct, yeah. Okay, so if f of 0 is equal to 0, then f dash to 0 is going to be equal to 1. And then what we have is basically a 0 state and the minus state. If we have it the other way around, if f of 0 is equal to 1, then f dash to 0 is going to be 0, so we've got minus the minus state. And this means what we have is minus 1 to the f of 0, 0 minus. So, because if f of 0 is equal to 0, this sign disappears and we just get the minus state. But if it's equal to 1, then we get minus the minus state. And then we can repeat exactly the same argument when the input is minus. So same state as here, but now the first qubit is a 1. Exactly the same state, but you're evaluating, this is going to be 1 and 1, and you're going to be evaluating f of 1. And then exactly the same argument as before. So if f of 1 is equal to 0, f bar of 1 is going to be equal to 1, so you've got the minus state. If f of 1 is equal to 1, then this is going to be equal to 1, and f bar of 1 is going to be equal to 0, and you've got minus the minus state. And what you can see is we've got exactly this out. We've got this expression out. And that's just going to be a useful expression in evaluating the action of the oracle. Okay. So now let's look at what state psi1 is. Oh, damn it. There is a typo here. This should be a state 1. Yeah. I can't bother to correct that. This should be a 1. I'll write it out again. Okay. So what is state psi 1 here? Correct, yeah. So what we have is psi 1 is just the action of Hadamard's on the 0 and 1 states, which is just equal to the plus or minus state. And then what we want to do is we want to evaluate the action of the oracle on the plus and minus state. And to evaluate this, we can use the expression that we have over there. So if we write this out, we can write it out as so all I've done is I've left the minus sign, the minus state as it is. I've not expanded that out, but I've expanded out the plus state. And now we can use the expressions over there combined with linearity to evaluate what this gives. So any takes on what this gives?
So it's minus 1 to the power of 0, 0 minus,
Yep,
plus,
correct.
minus 1,
Yeah.
of 1, and then it's 1 minus.
So all we're doing is, in fact, we've got, starting with the superposition of these, we know from the top line over there how this evolves under the oracle. We know how this evolves under the oracle, so when we take a superposition of them, we just get the superposition of the two outputs we had from before. Okay. Now, we can look at how this state actually is, depending on whether f of 0 is an odd or even function. So, what happens if it's even or constant? Can anyone see what state you get out in this case? So what does side?
Plus 1 minus up to a global phase,
Correct.
which depends on whether the constant is f of 0 and f of 1 equals to 0 or equal to 1.
And how can you see that is what you're going to get?
How can I see what?
That is the state you get out.
Because f of 0 and f of 1 are the minus 1 to the f of 0 is equal to minus 1 if f of 0 is equal to 1 or plus 1 if it's equal to 0. So
Yeah,
it's
or
like a computation.
if they're the same, then you're going to get the same sign here. And so you're basically just adding these. And if you're adding 0 and 1, you've got a plus state. And you can just pull it out the front. So effectively what you've got is 1 over root 2 So if f of 0 equals f of 1, this is just f of 0. Pull the whole thing out the front. You've got 0 plus 1. You've got a plus state. And what's this going to equal to? Well, it's going to be either plus or minus 1, depending on what f of 0 is. Okay, so someone who's not studied Deutsche algorithm before, can you tell me what you get when the function's odd? Correct, yeah. And the way you can see that is that if these two are different values, then you're going to get different signs here. So you're either going to get 0 minus 1, or you're going to get minus 0 plus 1. And so, yeah, you get plus or minus, minus, minus. Okay. So final step is just apply a Hadamard gate onto the first qubit. So what do we get in the two cases now? So we just need to know, well, nothing happens to the second qubit. The second qubit we're not doing anything to, that's going to just be minus still. And the first qubit?
0 minus or 1 minus.
You're not reading, no? You're not measuring.
You're not measuring yet.
No, so the plus becomes a minus.
Not for the Hadamard gate.
Plus becomes a 0.
The plus becomes a 0, correct. So the Hadamard gate, I mean, I just think of it as switching between the X and Z basis. I can never actually even remember what it looks like in gate form. I have to go to the Wikipedia page. I just think of it as it takes 0 to plus, plus to 0, and it takes 1 to minus and minus to 1. And that's just something you should have ingrained in your head. So for even, it takes it to 0. And for odd, I've just said, but does someone want to repeat what you get out? 1. So now, you do your final measurement, and, I mean, maybe to point out the obvious, yeah, it's 100% certainty. So if you measure the first qubit and you get it in 0, you know you had an even function. If you measure the first qubit and you get it in 1, you know you had an odd function. Or, one thing that is nice to note is that you can write this, so going back right to the start, remember that f of 0 plus f of 1 is 0, and if it's an even function, and f of 0 plus f of 1 is equal to 1 if it's an odd function. And that's exactly what we have out here. So you can just write the output state as equal to so you're effectively computing f of 0 plus f of 1, bitwise addition. Cool, so that is a summary of the algorithm. As you can see that there are sort of two ingredients you have here. So it's not just quantum parallelism. If you just do the quantum parallelism of feeding into superposition, then all you get out is the inputs with equal probability. So you're not going to be able to do better than classical. But what you're using as well as quantum parallelism is interference. So using the interference between the different inputs you put in, that you then interfere again with this final Hadamard gate. And it's through that that you're able to compute a global property. And note, you're still only getting one bit of information out at the end. It's not like you are learning what f of 0 is and what f of 1 is. But you're just being able to compute this global property in a single oracle call, rather than needing to compute the local property separately and then combine them to get the global property. And this is often sold as the intuition behind quantum computing, that in some sense you evaluate everything at once and then interfere it. But actually, where the power of quantum computing comes from is very much an open research question. So it's not just parallelism and interference. Oh, oops, my Slack's on. It is, and the reason we can say that is there's this argument that using only something called Clifford unitaries, so Clifford unitaries include C-naughts and single qubit rotations by a certain angle, so it includes Hadamards, it includes NOT gates. Using this set of gates that are known as Clifford unitaries, you can actually create arbitrary superpositions and have parallelism. You can also generate interference effect. And yet, the Gottesman-Nils theorem tells you that this set of unitaries are classically simulable. So there are many cases where you have both quantum parallelism and interference, and yet the scenario is classically simulable. So that can't be the full story about where the power of quantum computing comes from. You then have this highly technical field of research where people try and figure out, pin down exactly where it comes from, what it is that you can get an exponential advantage from, but not classically simulate. And one of the leading contenders right now is the idea of contextuality. So contextuality is basically the non-commutativity of measurement operators, the difficulties in predicting outcomes in different bases simultaneously. That said, I don't follow really that research that much. My intuition about where the power of quantum computing from is more in line with the stuff I was presenting yesterday. And that is quantum computers are really well suited to simulating quantum systems with exponentially large Hilbert spaces. They've got this exponentially large Hilbert space that you can do stuff in that is almost essential if you're trying to simulate or study other items that live in an exponentially large Hilbert space.
Could you please repeat what is contextuality and what they think that makes contextuality the thing that makes quantum computer strong?
Okay, so
I know you said that it's not in your intuition, but I didn't understand what you said.
okay, so in broad terms, I don't want to, trying to pin down exactly what contextuality is heated and gets very technical, and there are different ways of pinning it down. But a hand-wavy intuition is it's all about the difficulty in predicting different measurement outcomes simultaneously in quantum mechanics. So you can't, just because you know where something is in the position basis, you don't know where it is in the momentum basis. Or just because you know that it's where the spin is in the XY plane doesn't mean you know what the spin is in the Z plane, because the Pauli X, Y, and Z operators don't compute.
So you can only measure one of one.
Yes, and so okay, the term contextuality is, can you give a non-contextual description of the object? Or can you only give a contextual one that depends on what your measurement apparatus is and what measurements are being performed? And the point is, in quantum mechanics, you can only give contextual answers, you can't give non-contextual answers. It's context dependent. It depends on what measurement is being performed, whether you're measuring X.
What question you are asking the system exactly?
Correct.
Which is, so basically quantum computing is stronger than classical computing because in classical computing you can ask your oracle only a certain set of questions, while in quantum computing you can ask a broader set of questions. But the problem is that the answers that the oracle gives you depend on the context, that is on what question you ask him exactly, and you cannot.
Yes, though you're phrasing it in a negative way. The fun thing is actually that non-contextuality gives you power. The fact that you can't give it a contextual description is actually, in a sense, what makes quantum computing unique from classical computing, what isn't classically simulable, and what potentially allows you to achieve a speed up in classical computing.
Okay, thank you.
But yeah, as I say, I think particularly with a lot of the work being done at the moment, it's not obvious that contextuality is what's at play. I mean, there may be some sense in which it is what's at play, but the better intuition is that quantum computers are really good at simulating and storing exponentially large matrices. And that's particularly important if you want to simulate quantum systems. So for a hand-wavy sense of where the power of quantum computing is coming from, I would go with that intuition. And I think I'm going to end in a second, but one thing I'm just going to say before I do is that there is an extension of the Deutsche algorithm called the Deutsch-Jose algorithm. And so you see here, well, you can't tell we've got an exponential speed up here. For the Deutsche algorithm, it takes one evaluation when classically it'd take two. The generalization of the Deutsch-Jose looks at a bigger function. So it looks at a function that takes 2 to the n inputs. So it can take many, many inputs. And then the question, you're promised that it's either a constant function or it's a balanced function. So constant, all of them are 0 or all of them are 1. Balanced, of all the entries, you've got equal numbers of zeros and ones. And the Deutsche algorithm generalizes to solve that scenario too. Again, you can get away with just a single oracle call to figure out whether it's constant or balanced. But classically, you would need an exponential number. You don't need to look at all entries, but you need to essentially look at half the entries. And that's still exponentially many entries. So in this sense, the generalization allows an exponential speed up. Single cost evaluation instead of 2 to the n. And actually, I'm just going to leave it at that. And well, no, I've actually come to the end naturally. Though, yeah.
So
Were you telling me that I could overrun?
coffee break and food is going to be like 10, no, 5, 10, 10. So if you guys could...
I could start on Grover's and just keep on going.
Out questions, but like 10, 10, coffee out.
Cool. I will. Does anyone have any questions?
So why is it important for us to know function is even or odd?
It's not, really. That's what I said at the start. That's my misgiving with teaching Deutsch's algorithm. Like, it's not practical. It's a proof of concept. It allows you to get a sense of quantum parallelism, then see that quantum parallelism isn't sufficient, see that it's possible to get this exponential speed up quantum mechanically. That's the idea. And also, it's historically important. It was the first quantum algorithm that had an exponential speed up. But if it seems abstract and not important, fine. That's how it is. Any more questions? Any just like little bits of the calculation that you didn't follow that you want me to go over again? I could happily repeat that.
Obviously, the oracle is built up of other gates, because that's one thing which often is missing when reading these things. How are the oracle made?
Okay, so that's a really good question. It was one I was slightly nervous that people would ask, because there's an easy answer and a hard answer. So there are 2 different ways in which you can see it as built up of gates. You can just suppose you know what f of x is, then it's straightforward to actually construct u of f out of gates, and I can run through an example of that. What's less trivial, but is still possible, is say you have this box classically. How can you basically take this classical box and build it up into the quantum reversible gate? And that is possible to do, but it's less trivial.
But if you have it classically, wouldn't you still have calling the same function multiple times? If the oracle is classical.
Well, this oracle is classical in some sense.
But if it's classical.
Okay, no.
You're calling, I mean, if you're in a superposition of 4 states, you have to call it classically 4 times.
Yes.
So you're not getting the speed up which is required.
Yep. So the easiest way to answer this question is to see how you would build this out of gates. What's harder to see is how you'd build it out of gates not knowing what f of x is in the first place. But let me maybe spell out actually how you'd build it up out of gates, because I still think that makes it a little bit less abstract. Okay, so it's going to depend on exactly which function you're looking at. And I can't remember which are the simplest ones, so I'll just start with this one. So suppose it's an even constant function, even function where they're both 0. So now we can just look at what the action is going to be. So let me move it. So just looking at the box on the right-hand side, what we have is 0, 0 goes to 0, 0. 1, 0. So what I've done is I've just followed our sort of table from earlier, and I've substituted in these values of f0 and f of 1. So f of 0 and f of 1 are both 0, so then the opposites are just, the opposites are just going to both be 1. And then you can say, well, what gates do we need in order to do this? And well, this one's super simple, it's just identity. Yes, correct. But this one, I think...
Because in this case, the oracle is the function that you're trying to find. Correct?
No, because this is not an identity function. And it's not identity on the level of the single input. Because if that was the case, you'd get f of 0 equals... This is more the identity on the single inputs. But I think what we're going to find here is that you get a C naught. But we can spell it out again. Okay, so we have 0, 1, and then 1, 0. So we're saying that f of 0 is 0, f of 1 is 1, and then we're going to have the opposite around here. Okay, so yeah, this is a C naught. So if the first qubit is in 0, you do nothing. If the first qubit is in 1, then you switch them around, you do a naught. And for the other two, I think what you get is you get just a naught on the second qubit and then a not C naught, something along those lines. So you can, just by breaking it down to the action of the basis states, break down this oracle into gates. And the thing to note is that, as I said before, these are classically implementable gates. You're not creating any superpositions here. So they're unitary, they're reversible. So you apply 2 C naughts, you get back to where you started. But they're not creating any, in and of themselves, they're not creating superpositions. And in that sense, the oracle is a sort of classical entity.
Okay, but it works on...
But you can feed in quantum inputs.
It works on quantum gates, but there's no superposition.
Yeah. So a C naught, if you feed in a plus state, you get a Bell state. So you get this highly entangled state. But if you just have it acting on a basis state like this, nothing quantum mechanical is happening.
Could you repeat the point you said before about constructing a quantum oracle starting from the classical one?
Yeah, so this is something that I, to be honest, don't fully understand and want to understand better. I think the question is, the problem with this argument I've done here is it kind of assumes knowledge of the function in the first place. And ideally, if we're going to run this algorithm, we want to have a way of we don't want to assume knowledge of the function in the first place, otherwise it's all redundant. If we knew the function, we wouldn't need to try and figure out whether it's odd or even. So then the question is, how do you, without knowledge of the function, create some kind of oracle that acts in a reversible way, effectively takes this irreversible oracle and generates a reversible oracle out of it. And off the top of my head, I don't know the algorithm to do it. There is one to do it using, it's controlled gates, so you apply the function in a controlled manner. But then sorry, what's your name?
Evan.
Evan made a good point, that you can't assume that your construction includes something that's inherently classical that can't take quantum inputs. Otherwise, it's not going to work with the algorithm when you feed in quantum inputs, which is something I'd not thought about before, that I started to actually want to think about more. What? I've not thought about it before. How you would actually conceive of this box, whether you'd need to conceive of it to be able to take quantum inputs or not. I think you would. I think the idea is it would be something that's irreversible. And when you put in your quantum input, it sort of collapses the superposition in some ways. But yeah, something I want to think about more. It's a good question. I can point you to a chapter in Nielsen and Chang where they discuss this, if you want to run. In Nielsen and Chang? Do you know Nielsen and Chang? It's the Bible of quantum information theory. It's green and red and blue. Yeah, I think mostly green. So they have a section on how you construct, how you could construct an oracle just from the sort of the classical function evaluation. But I think for now, just thinking of it in terms of these sort of identity gates, C-naughts. I mean, one way you could think about it actually is that, so you're going to have 4 different UFs. You're going to either have identity, you're going to have C-naught, you're going to have like a knot, or you're going to have the not C-naught. And you could just say that you kind of pick, you have all 4 of them in a box, and you pick one of them out.
But so far, I always thought that we didn't think about the problem of elevating a classical oracle to a quantum one, because we simply wanted to count how many times we have to interrogate it, but without...
Yeah, when I was taught it, I was always taught it as a given. Literally, it was only when I started preparing this lecture that I started thinking, wait, well, how would you translate it from a more conventional classical setting where you have something you can evaluate f of x? But yeah, I think probably the way to think about it here is you have 4 oracles in a box. They're each made out of these gates, and you pick one of them at random, and you're trying to figure out which one you've got.
I have a question. So from this example, how do we see in this example that the speed up is...
Okay, so you can't here with a single, we only have n equals 1. So you've got a single data point. You can't tell the scaling with a single data point. So you have, then you have basically 1 versus 2. And that could be absolutely any scaling in the world. A single point, fit any function you want to it. The only way you see the exponential scale up is when you get onto the Deutsche-Jozsa algorithm. And that's when you have an input that it's going to be 2 to the n dimensional. So x is a 2 to n dimensional vector. And what you see then is that with the Deutsche-Jozsa algorithm, you can still get away with a single oracle evaluation, so 1. Whereas classically, if you're trying to figure out whether it's constant or even, most naive method, evaluate all elements, so that would be 2 to the n. You actually don't need to evaluate all 2 to the n. If you evaluate half of them, and then 1 more, and they're all the same, then you know it's not balanced. So a balanced function is when half are 0 and half are 1. So if you get 2 to the n over 2 plus 1 entries that are all 0, you then know that it's definitely going to be constant. So that's when you see the exponential speed up, constant versus 2 to the n over 2 plus 1. Any more questions? I think probably, given the time, may as well save Grover's now to the next talk, and just got a bit of time before tea in 7 minutes' time.
I have a quick question. Sorry, because I came late.
Sure.
On this truth table over there, of this transformation you do from the input 0, 0, 0 to 0 function of 0, then 1, 0.
Wait, sorry, what you're talking?
Yes.
This one. Cool.
So that follows just this block on this side.
Yeah, it's this.
So it means that on the right-hand side, so the last 2 are evaluating, for example, this 1 C naught F0 and the other 1 C naught F1.
Yep.
But up it should be then 0 C naught F0.
No, these aren't C-naughts. These are bitwise addition. This is bitwise addition.
Bitwise addition. Okay, so that's why the zero is not pointed out on the first two. Exactly, there.
Yeah, yeah. So what you're doing is this. So if you've got 0 plus f of x is just f of x.
So it's okay. It's like
Yeah. So I could have had another line here. I could have done 0 o plus f of 0 equals f of 0. Yeah.
O plus is like an OR. XOR. Okay.
Yeah. So, I mean, the truth table for it is here. So 0 plus 0 is 1, 0 plus 1 is 1.
Now,
Yeah.
Yeah. Okay. Is there a way to go
Sure. The high-speed version.
that was and yeah, thank you very much. Take a picture. Those really
Okay.
I appreciate it.
Right. You're free to go. So in this lecture, I'm going to cover Grover's algorithm. You graduate from simple examples in the Nielsen and Chang textbook to the main algorithm section. So it's a little bit more involved, but not massively more involved. It's also a teeny bit more practical, but again, not that much more practical. I still think something like simulation is a more exciting quantum algorithm, but I'm biased, obviously. Okay, so Grover's algorithm. So this is a search algorithm. So the classic introductory example that people always use is, imagine you have a phone book and a mystery number you found on a bit of paper, and you want to try and figure out the name that goes with the phone number. So you're kind of doing an inverse. I don't know why this is used as a classic example, because no one uses phone books anymore, but I guess when Grover's algorithm came about, which I think was the 90s, maybe people still used phone books. Okay, so the idea is you have, and actually you can use more exciting examples. So I think the example that they start Nielsen and Chang with is a sort of traveling salesman-like problem. So say you have a whole bunch of different cities and you're trying to figure out the shortest route between the different cities. How long is it going to take for you to search to find the shortest solution, given that you have something that can tell you whether or not something is the shortest solution or not? How many different options do you need to search through? Okay, so we're going to suppose that our phone book has 2 to the n entries in it. So there are 2 to the n different items that you're trying to search among, and there are m solutions. Okay, and classically, naively, just for a generic search problem, it's going to take around order n evaluations in order to get there. So you're going to just have to search through your book one by one. So on average, it's going to be off order n, 2 to the n different entries. But quantum mechanically, we have a quadratic speed up, and we're going to find that actually you can get away with just square root of n calls. So classically, you need to look them all up. It's going to be, the scaling is going to be order n. Quantum mechanically, what we'll find order square root of n. And as before, we're going to formulate the problem in terms of a function. So we're going to say that we have some function f, and f of x equals 1, if and only if the input x is a solution. I'm going to denote the set of solutions with a curly s. And that the function equals 0 otherwise. And I'm going to call the set of entries that aren't the solution, I'm just going to denote that with a curly t. So if x is in t, f of x equals 0. If x is in s, then f of x equals 1. Wait, can you put the screen on? Thanks. And as before, we're going to suppose that we evaluate this function using an oracle. Okay, so exactly the same oracle as before, and I'm going to again use this sort of arrow notation. So what we have is that xq under uf goes to x where again, this is bitwise addition. It's bitwise addition and not tensor product. Someone was confused by that after the talk. It's important to note that O plus is not the same as O times. Cool, okay. So just to sort of really drive it home, as we saw before, if you put in 0, this sort of bitwise addition doesn't do anything. So what you've got is x and f of x. So again, we saw this before, but if you feed in 1, then you're going to get 1 O plus f of x, and that's just basically doing the opposite. So if my overline is just if f of x equals 0, then f bar of x is going to be 1, and vice versa. So it's a NOT gate, effectively, my overline notation. Cool. Okay, so now let's look at okay, and I'm just going to do another helpful identity for what this oracle function does that's going to come in useful once we get onto Grover's algorithm. So we're going to suppose, let's look at what happens. No, we actually had this before. So we saw before that if you have x and then minus, do people remember this from the previous lecture, or shall I just drive it home by going over how you get it again? You want to go over it again? Cool, I can happily do that. So what we have is so I've just expanded out the minus state. It's just basically 0 minus 1 with the root 2 out front. Okay, and now I'm going to use these two expressions. So x0 is going to go to x f of x, and x1 is going to go to x f bar of x. Yeah, that's correct. Okay. Now we have two options. So let's suppose that f of x is equal to 0. Then f bar of x is going to equal to 1. And you know what? Someone else is confused by this. I'm going to spell it out really explicitly. Okay, so if f of x equals 0, we just have 0 and 1. So we have a 0 minus 1. We can pull this x out the front, and we've just got a minus state there. So in the case where f of x is 1, exactly the same, but we get 1 and 0, which is the same as that, but with a minus sign out the front. So we've just got minus. Oh, wait. I don't need this 1 over root 2 here. The 1 over root 2 gets absorbed into the definition of the minus state. So, and then if you just want to write this more compactly, this is equivalent to minus 1 to the f of x, x minus because if f of x is equal to 0, then this is just a positive sign. If f of x is equal to 1, then this is a minus sign. So we get these two back out. Cool. So what this means so if x is one of our solution states, then we have f of x is equal to 1. So in that case, what we have is by the way, I will continually switch between writing them as two separate kets versus putting both symbols in one ket. They mean exactly the same thing, it's just habit to some extent. I'll explain why in a second why I've done it this way, in this case. Okay, so if x is in S, then we have f of x equals 1, in which case we get this minus sign out. If it's not in S, we have f of x equals 0, and we get the positive sign out. And the reason I suddenly started writing it as separate kets is you can see that this minus state basically factors out. It's not really doing anything, it's left unchanged. So often we can just drop this. We don't really need to look at the action of the minus state. It's not having really an effect. And crucially then what you see is that under the action of the oracle, x changes sign if x is a solution, but it remains constant if it's not a solution. So the oracle marks out the solution with a change in sign. And this is important, so I'm just going to put it in a blue box. I see a couple of confused faces, but are you good? You're good? Cool. Right. So, okay, that's enough on the oracle. Now on to how the algorithm actually works. Okay, and I've sort of listed, I guess, the recipe on the board, but I'm going to talk through it more slowly. Okay, so first thing you do, prepare the all zero state. If you've not seen this notation before, when I do O times, when I do to the, almost like to the power of O times n, I just mean n copies of the zero state. And sometimes I might be lazy and drop this, but you've just got to remember that it's acting on an n-qubit state and it's just all zeros now. And then what you're going to do is you're going to apply Hadamard's to all of the states. And we know, sort of crucial thing never to forget, is that the action of the Hadamard on the zero state gives you the plus state. Yes?
This question is not very important, it's just one thing about notation, but why every time that we have an algorithm, we always prepare the zero state and then, say, apply this gate to manipulate the state instead of just saying, I don't know, prepare the plus cross n state?
You could.
Not just QE, it's basically everywhere I have read so far.
It's not, okay, so I thought about saying for this, just prepare the all plus state. You could say that. It's because actually on a quantum computer, on most quantum computers at least, you have one particular state you can initialize into. And you call that the computational basis state. And then all the other states you need to apply gates in order to prepare. So that's why it's just good to basically explicitly state all of the actions you need to do. That's what you have in these kind of algorithms where you're sort of really spelling everything out. You saw yesterday when I talked about quantum simulation, I often said, okay, let's just say you start in some state psi naught. And that might be because your psi naught is something generic that comes out of some other algorithm and you don't actually even know how to prepare it potentially. But yeah, here I'm just going to spell out each of the states because you prepare your ground state, well, you prepare your all zero state basically by, oh God, I don't know enough about how these different works on different devices, but it's roughly like cooling to the ground state.
Because of experimental
Experimental necessity means that you can initialize in one state and then you start applying your gates. Cool, okay. So, what is this equal to? If you're just applying Hadamard on each of your initial states, correct, yeah, you just get n pluses. Which again, I'm just going to write with this O times n up there. Okay, and now, what I'm going to claim is that this thing is equal to a uniform superposition over all possible inputs. And I think when I was taught this, it was just assumed that this was obvious. But I remember it not being obvious to me. So I'm going to spell it out by my favorite form of proof, which is run through the n equals 1 case, the n equals 2 case, and the n equals 3 case, and then spot the pattern. Because, I mean, it's not a good proof technique, but it's how we do a lot of research and practice. Okay, so the plus state is just 1 over root 2, 0 plus 1. So those are all the possible states you can have on a single qubit. Okay, can someone expand this out for me? What do you get? Classic. It's early. Correct, yeah. Okay. And what we often do is we often just say, I'm just going to sort of oh, I guess I haven't. Okay, and then for n equals 3, so now we're going to have plus, plus, plus. So the plus, plus we've already done, so we're going to have a half, 0, 0. And now we get 8 different terms. So now you can see if you chuck this one in, you basically add a 0 to the end of all of these. So you're going to get 0, 0, 0, plus 0, 1, 0, plus. Actually, I'm going to do it slightly differently because I think it's easier to... oh, whatever. I'll run through it. Yeah. Zero, 0, 1, plus 0, 1, 1, plus 1, 0, 1, plus 1, 1, 1. And you'll notice that we've now got all possible combinations. So we have, and this is why I hesitated for seconds, I want to do it in a different order. So this is basically the number, so we've got 1, 2, 3, 4, And so these are just, we're just adding up bitwise. So what this notation up here means, this x is just basically a number expanded in binary. So what we're doing here is we've got 0 equals 0, and then we've got 1, 0, 1, 2, 1, 0, etc., etc., etc. And so what we get when we when we have this plus to the n is we've got an equal superposition of all possible combinations of qubit states, basis states. And we can just represent all these different combinations of qubit states as a single number. So switching from binary to just standard counting. And how many do you have? Well, we've got 2, 4, 8. You've got 2 to the n. So it's going to be an equal superposition over 2 to the n different values. So they all happen with probability 1 over square root of 2 to the n. And if you remember right at the start, we just said that n is equal to 2 to the n. Cool. So that's what we get out after step B. And I'm just going to call this state psi, because it's going to appear again and again. It's going to be useful to have a shorthand for it. Okay. Now we get on to C. So now we apply the Grover's operator, and this is where things get a little bit more confusing. So this is what the Grover operator is. What you do is you apply the oracle, you apply UF, then you apply Hadamard on all your qubits, then you apply this thing, this is a funky term, and then you apply Hadamard on all of them again. So that's the sequence. Okay, so let's look at what I think 1, 2, and 4 we're familiar with.
The oracle takes more than 2 inputs.
Ah, yes. Wait, sorry, what do you mean?
Because the function that we worked out with the 8 terms has 3 inputs, right? 0, 0, 0, 0, 1, 0.
Ah,
Zero is the zero tensor, and it's not the zero in the bit basis, but it's the zero in the number basis from x equal to 0 to x equal n minus 1.
yes, that is confusing, because x is kind of taking I'm switching from talking about x in terms of bits to talking about x as a number now, which is often done in the literature, but it is confusing notation. And also, I guess the other thing to note is these wires don't need to denote a single qubit. They can denote, and so typically this x is many qubits. So it's sort of many wires together.
All right, okay.
And sometimes, I wish I could draw on this, but I'm not going to destroy the fancy TV. The notation they use is like a slash and then an n to denote that actually that's n qubits. Okay, so 1, 2, and 4 we're kind of happy with. 3 is the new element here. So let's have a look at what it does. So if we apply it to, and again, okay, these are both O times n. I have dropped the O times n, but they're actually acting on the n qubit system. So if we, maybe I'll write it with the O times n on the board here just to make this clear. Okay, so can anyone see what we get out when we apply it to the all zero state?
Plus 0, 0.
Okay, so spell through how you get that.
Eh?
How'd you get that?
Because the projector is 1 on that state and 0 on any other state in the computational basis, while the identity is always -1. So for that particular state, you have 2 minus 1 equals plus 1.
Yeah.
For all the other states, you have 0 minus 1, which is -1.
I was just going to do it on the zero state to start with. So what we have here is If we expand it out, when the all zero projector hits the all zero, you're just going to get all zero again. So maybe I can write it really explicitly. So this is just going to be 1. 0 hitting 0 is just 1. Identity hitting the all zero state is just going to be the all zero state. So you just get out the all zero state. But so what do you get here? Get 0, correct. If I is not 0, yeah. And that doesn't do anything. So you just get minus your input. So what this operator does is it applies a phase of -1 to all inputs except the all zero input. Cool, okay. So now, just to be explicit, okay, so the Grover's operator takes this form. I'm sort of, O here is equivalent to UF. I have a sort of proliferation of notation. It should just be the same thing. The thing to notice is, so if we have H, O times N, so this Hadamard, you can bring through and hit the all zero state in both cases. And so can anyone see what a better way of writing this? Yes, but it's plus O times N. So it's N pluses. And that N pluses is that equal superposition state we had before that I'm going to denote with psi. And the Hadamards that hit the identity, nothing happens. So just Hadamard squared is just identity. So you can just drop the terms there. Okay, so that is the total action of the Grover's operator. Okay, how am I doing for whiteboard space? Okay, and this is where it does get a little bit funkier, because the way to understand this Grover's operator is geometrically. You understand its action geometrically in a basis of states that are basically the equal superposition of solution states and equal superposition of states that aren't a solution. So I think bear with me as I introduce some definitions now, and hopefully it becomes clearer once I start to sketch out what's going on. Okay, so I'm going to define the state S, which is the equal superposition of all the solution states. And the state T, which is the equal superposition of all states that are not a solution. So remember, there were m solutions, which means there are n minus m non-solutions. Okay, and now remember the state we get out after preparing the all-zero state and then applying the Hadamard's is the all-plus state. And this all-plus state was the equal superposition over all possible inputs that I called psi. And now what I want you to notice, so psi is we're going to write this state psi in terms of these states that I've defined, the equal superposition of solutions and non-solutions. And the way you do that is you just split up this sum into the sum over solutions and sum over non-solutions. And now this is just that up to a normalization term. Ditto that is that up to a normalization term. So just sort of basic algebra, we can write this as, so if you multiply this through by square root of m, you're going to get this thing out. So this first term is just going to be square root of m over n times s. Same game for the second one. So this is what you get if you multiply that through by square root of n minus m. Okay, so this is where the geometric picture starts to come in. So we can write this state psi in the sort of the st axis, in the st, the directions defined by s and t. So this is just going to have coordinates m over n, and this is n minus m over m. And at first it's not clear why you're going to do this, but it will hopefully become clear in a second. It helps you understand what happens when you apply this Grover operator. Okay, so the first thing we're going to think about is what happens when you apply the oracle. Now, when you apply the oracle, from before, we have that x goes to minus x if it's a solution, and x just goes to x if it's not a solution. So what this means is you're going to have that s goes to minus s, but t is is just going to go to t. Is that clear? Cool. Write it up here too. So, the O. So we can represent this geometrically. So we're going to have s goes to minus s. So we're going to have well, actually, let me write it all out. So if we have O psi, if we've got psi over there, what's that going to equal to?
Minus M1 S.
Correct.
M1N.
Yeah. So what we now have is this state. So the t value is left unchanged, but now we're on minus m over n. So what we've got is a reflection about t, about the t-axis. That's the action of the oracle. Okay, so that's what happens when you apply the oracle. Then the question is, what happens when you apply this? And what it does, and this is a little bit harder to see, is that it performs a reflection about psi. And I think the way to see this is to note that the overlap with psi is left unchanged by the action of this operator. So let me just spell that out. So say you have some state phi. You then apply that to psi minus identity. And then let's look at the overlap with psi again. Can anyone see what this is going to be equal to? Yeah. Well, no, not 2 psi phi. Well, the first term is 2 psi phi. Yeah. So this just gives you 1. So you get 2 psi phi minus psi phi is equal to psi phi. So the overlap is the same whether or not you apply this operator. And this implies that it's just a reflection about psi.
So we get minus square root n minus M1N. Am I mistaken?
I can't actually see what it is straight away. I was going to draw it up, and then you can figure out what it is geometrically. So what you're doing is you're now reflecting about this. So I think that's going to take you to somewhere around there. And it's easier to see once you draw the angles in. So because my drawing's not very good. So let's just suppose that's theta over 2. I'm just going to define this as theta over 2. Then that angle up there is going to be theta, because you're reflecting about that. And this state up there, well, that's just going to be equal to 2 psi minus identity O psi, which is just equal to G psi. So that's what you get when you applied it once. Okay. And what we can see is that basically the combination of the two reflections is a rotation, and more importantly, it's the rotation that's taking you closer to the solution state.
You can probably write phi in terms of M1N.
Correct, exactly. You now do a bit of trigonometry, and what you can do is you can figure out how much you've rotated by and how many rotations you need to do to get to S. So that's what I'm going to do now. people done with this board? Do you mind if I wipe this one? Actually, I can probably do it on here. I'll do it here. Maybe it's the coffee, but my handwriting's grown in this one. Okay. So let's first use this kind of geometric representation to rewrite the state psi. So I just introduced that theta over 2, and I'm just going to rewrite psi in that form. Basic trigonometry. Now, the action of g on psi is, well, it's the same as before, but we now have this angle, which is going to be 3. Well, it's yeah, theta plus theta over 2 equals 3 theta over 2. And actually, every time you do a rotation, you get an extra angle of theta. You keep on rotating. Every time you apply g, so you do your 2 reflections, you rotate by an angle theta, which means that g to the k theta is equal to cos k theta plus theta over 2. So we can write the state after k applications in this way. This is probably easier to picture in the case where m is much smaller than n. In that case, this angle theta over 2 is going to be very small. And you can see that with each application, you're just going to get closer and closer to s. Probably would have been better to draw it that way to some extent. Let me just sketch it in the corner here. So you've got t and s, and say your initial state here is psi with square root of m over n being small. So here we have m much less than n. So you can see that each rotation is just going to get you a little bit closer.
What is exactly m?
M is the number of solutions you have.
So you can have multiple solutions.
You can have multiple solutions. So the simplest case is where m equals 1 and n is big, in which case m over n is tiny. Okay, so the question is, what k do we need in order to get as close as possible to the solution? And this is where I'd like more colors than I have. It's a shame that red's not working. But let's just call this angle here phi. So this is the angle that you want to rotate your initial state psi through to get to the solution state s. Because ultimately, we want psi to become s, because then you can measure it, and you're certain to get a solution. So what we want is psi equal k theta. So psi is the angle we need to rotate through, and theta is how much we rotate through with each application of g. Okay. So now this is where we start doing some trigonometry. So what we have is that cos phi. Okay, so can anyone see what cos phi is? Well, I guess there's
I would say n minus m. You took the
Something's gone wrong there because it should be m over n.
I think you've written it mistaken. N minus m on n should be on the horizontal line.
That should be it, but that's not. That's not what the problem is. What we should actually have is this. But that's not what I'm getting according to my chart, my graph. Give me 1 second.
This should be s at the t then.
I think you use the fact that phi is equal to 90 degrees minus theta hat, and then you expand for small angles.
No, even before you get there, you should be able to see it from this. Because you should be able to just work with this triangle.
Maybe you switch the s and the t axes.
Oh, no, no, this is right, isn't it? Adjacent over hypotenuse. No, sorry, it's fine. You just confused me when you said it was n minus n. So what we've got is cos phi is equal to m over n minus 1. Yeah, you just confused me. This was right the whole time. But at least now we've thought about it hard enough, it's now obvious. Cool, perfect. Have me worry for a second then. Yeah, basic trigonometry, 101, sort of age 14. We have cos phi is equal to this divided by that. Perfect. So, okay, what we have then is phi is equal to arc cos root m over n. And so k is equal to phi over theta, which is equal to arc cos root m over n over theta. Of course, in general, this won't be a whole number, so you're going to want to round down. But this gives you a good estimate of how many rotations you need to do. And what it is. Okay, so let's now just, arc cos is a bit of a pain to work with. It's hard to have a handle on what arc cos actually is. So let's assume that m is much less than n. So in that case, phi, which is this, is just approximately equal to pi over 2. Yes. And theta equals question mark. Again, basic trigonometry. We're going to use sine theta over 2 is approximately equal to theta over 2 when theta is small. And we know that sine theta over 2 is equal to root m over n. Basic trigonometry. So what we have is that theta is equal to, well, approximately equal to 2 root m over n. And therefore, k is equal to pi over 4 times root n over m. And this is order root n. So remember right at the start I said that you weren't going to need n cools, you're going to get away with square root of n cools. Well, this is a square root of n cools that you're getting away with. How am my blue pen? How have I lost all my pens? Aha. And the final thing to look at is the probability of success, or more pessimistically, the probability of error. Because we're rounding here. We're rounding here, so we're not going to perfectly align with S. If this is a whole number, then you're going to end up, after your k rotations, you're going to end up perfectly on S. But typically, it won't be a whole number. In which case, you're going to end up, and I'll draw this over here. So you're going to end up some distance away. And because you're rotating by theta each time, how am I doing for time, actually, by the way? Doing okay. Because you're rotating by theta each time, the biggest this error can be is theta over 2. So your probability of error is just going to be sine theta over 2. So it's basically the amount, well no, your final state, I'm going to call it phi final, is at worst something like cos theta over 2s plus sine theta over 2t. So your error probability and we said as before, sine squared theta over 2 is equal to square root of m over n. So this is going to be m over n. So if you are only trying to find a small number of entries in a big phone book, your error probability is going to be pretty damn small. And I think that's everything that I really wanted to cover. So does anyone have any questions?
Obviously, at the end, you need to measure
Yes.
in order to get. So I understand. If there are multiple solutions, how can you arrive to them?
You're going to find one solution each time.
So
So you'll find a solution.
you find one.
Yes. And then you run it again and you get a different solution. And you're going to get each of the solutions with equal. Yeah, or you can get the same one. So each time it's equal probability of getting any of the given solutions.
And the problem with actually Grover's algorithm, because I tried to do it theoretically, and most examples, they assume that your unsorted list is actually 1, 2, 3, 4, 5. It's not sorted. It's not unsorted.
Say that again?
The scope of Grover's algorithm is to find the solution in your, let's say, have a set of numbers.
Yep.
From 1 to 10.
Yep.
And you need to find 5.
Yes.
Okay? But it would make sense if it is unsorted. Most samples, most tutorials, when they try to do, for example, in Python, when they try to do the Grover's algorithm, the unsorted list is actually sorted.
Yes.
So because they're trying to do a proof of concept rather than giving a solution. So one problem is that you need as much qubits as you have entries. What I'm saying is that you need a lot of qubits, no, to create the oracle.
No, because you can create them. So remember we had so 0, 0 is going to correspond to 0, and 0, 1 is going to correspond to 1, and 1, 0 is going to correspond to 2, and 1, 1 is going to correspond to 4. So if we've got 4 entries, you only need 2 qubits.
Yeah, but if you have, I don't know, like the number of qubits always have to increase.
So you're going to need n qubits. So when if you've got n entries, you're going to need n qubit. So you're going to need log capital N. So that's a sort of exponential improvement on the classical case. Of course, how you encode it, how you get your classical information and encode it into your quantum state is another question. Because you're going to have the classical information being exponentially large in the first place that you try and get into the quantum state. And that's one of the biggest problems. Again, I go back to why I care more about quantum simulation than Grover's algorithm, is when you're trying to do these kind of classical tasks, you've got to translate your classical problem onto the quantum computer in the first place.
Translating, you find the solution.
Potentially, yeah. So I...
This works in the future where there are quantum databases.
Yes, because if you're trying to get your classical database onto your quantum hardware in the first place, that means you've got to be able to handle your classical database in the first place. That said, in this case, for Grover's, maybe it's not so crazy. Like, it's okay having a massive phone book, but looking through each entry in the time one by one is a pain. You might be able to store the information, but searching through it is annoying. But still, I think the point stands that quantum computing is way more interesting for inherently quantum problems than classical problems. My biased opinion.
About what the earlier question was, about finding all the solutions in practice, right? So it would probably also be a problem that the solutions are all in a superposition, so you would need many more than m repeats because you would keep getting duplicates.
Yeah, I mean, I think it depends what you're trying to do with your... So you get your solution state out at the end. And if you just want to sort of evaluate each of the solutions as to go, then yeah, you've kind of got this quantum parallel problem that is stuck in superposition. But say you actually want to compute some global property of your solutions, then you might be able to feed it into another algorithm and get that all in fewer oracle calls.
You don't actually need to measure in the end.
Well, you're always going to need to measure at the end. But if you've got this solution state, and then you want to kind of compute some other property of it, you feed those solutions into some other function, and you want to tell whether it's odd or even, you can do that. So yeah, I guess again, it's an abstract idea, but actually in the case of Grover, it's to some extent it's less abstract than Deutsch, in that things like Grover's are often used as subroutines in more complex and useful actual algorithms. A cool one is, and I don't know the details on this, but you can actually formulate quantum simulation as a search algorithm. You can actually formulate quantum simulation as a search type algorithm. You can show that they're almost equivalent. And it's not something I've ever worked on or looked into, but it's something that's often said.
If there aren't any more questions, we can move on to the next lecture.
Cool.
Time.
Sure.
Maybe just
So, hi everyone, welcome to today's Qiskit 101 session. So I'm going to have basically 3 different parts. In the first part, we're going to see what the IBM Quantum Composer is. So that's a very easy way to interact with IBM's quantum computers. It's very straightforward. You can just drag and drop some gates. You will see that. Then in the second part, I'm going to show you how we can do more advanced things, so how we can actually program using the IBM Quantum Lab. So I will show you first how to do basic circuits, but then we will also implement Grover's algorithm, which is the one that Zoe was just introducing. And then in the third part, I would just very quickly introduce to you what the IBM Quantum Community team does, which is the team that I'm working for, and so how you can learn more about, in general, quantum computing and programming with Qiskit. Is it actually fine the way I sit, or do I, somehow? Like, people can still see what's behind me, right? I'm not... Or should I move around a bit? I mean, I might also just sit on the side or something, but... okay, so just very quickly to... I can also stand. What's Qiskit? Qiskit is an open source framework development kit. So it's written in Python 3, and it's what we use to program IBM's quantum computers. So let us start with the first part, where I show you the quantum composer. If you want, you can all go to quantum-computing.ibm.com. I really highly encourage you all to make an account there, because later on we will have the joint session together with TKIT, so with Quantinuum, where we can all program directly using, they also have support for Qiskit, so you can use Qiskit and TKIT and program the devices. And I have reserved 3 different devices where you can just skip the queue and directly go in. But for that, I would need your email addresses that you have to create that you're using to create an account. So I got from Jake the email addresses that you registered with for the conference. If you use those to create an account, I can add you directly. If you have a different one, just tell me which email address you're using. So if you go to quantum-computing.ibm.com, it should take at most a minute to create that account. It's really straightforward. Of course, I already have an account. Sorry, let me actually do it like that. No. Wait, but I just removed the power, not the cable. Okay, anyway.
I can connect this to remove the cable. Remove the hanging cable.
Yeah. Well, I guess it's fine like that now. But thank you. So, yeah, feel free to do it now. If you want to create an account now, I might just give you like a minute, so you can do that if you want. Otherwise, you can just relax for a minute. And we will figure out the thing here. Oh, thank you. Again with the pen. Okay. Thank you. So is that fine? Then I'm hopefully not anymore sitting in front of the screen. Yeah. Okay. Thank you. Okay, so here you can see this is the landing page, and as I told you in the first step, we will try to play around with the IBM Quantum Composer. So I can just click on Quantum Composer, and then automatically this thing will open. We can see here there's 3 different lines that correspond to 3 qubits. If I want more, I can just do that, or remove it again, add as many qubits as I want. And now I can just take a gate, let's say the X gate, and move it here to whatever qubit I want to apply to. So now we can see, actually, the probability is now updated. So now it would, with probability 100%, be in the state 001. 001 is because with Qiskit it's somehow reversed, I think a bit counterintuitive, but it's like binary numbers. So qubit 0 is the one that's on the very right side. So qubit 0, because we applied an X gate, will be in state 1. And qubit 1 and qubit 2 will be in state 0 because I haven't applied any gate yet. Then I can just remove that gate and, for example, take my Hadamard gate. Remember, the Hadamard gate brings me in a superposition of 0 and 1. So we can see here, now I would be in a superposition of 0, 0, 0 and 0, 0, 1, because I haven't done anything to the other qubits. Both I would get with probability 50%. Of course, if I apply a second Hadamard gate, I would go back to the 0 state. But now I could, for example, also apply different Hadamard gate, 3 Hadamard gates to all my 3 qubits. And we can see now the probability is 1/8 for each of the 8 different bit strings. I can also add some phases. So for example, an S gate, or a T gate, or a Z gate. And what you see on the right side, the probabilities don't change because it just gives me an extra phase. But the extra phase, since I just measure, it doesn't matter whether the state is 0 + 1 or 0 - 1. If I measure in the Z basis, which is automatically what I would do, it doesn't change the probability of measuring either of the bit strings. But what we can see here on the right side is what we call the Q-sphere. The Q-sphere should not be confused with the Bloch sphere. It's a different thing. The Bloch sphere we learned is a way to represent 1 qubit. Here the Q-sphere is kind of a generalization where we can visualize all our big qubit state on all qubits. And we can see here that each blob corresponds to a state. So we have 0, 0, 0 at the top, 1, 1, 1 at the bottom, and then those states with 2 1s here at the lower level, and at the higher level we have the ones with 2 zeros and 1, 1. And the different colors indicate the different phases, which came from the gates that I was adding here. So if I have no phase gates, it's all blue because nothing has a phase. If I add, for example, a Z gate, then I'm getting a phase of pi, that's why it's red, on the first qubit, so on the one that is on the very right side. So wherever I have a 1 here, I will get a red state, and so on. Let's try then also to do some entanglement, create some entanglement. We know in order to create the ball state, for example, we apply first the Hadamard gate, and then the C0. And we can apply another C0, and then we get to the so-called GHZ state, so to the state 0, 0, 0 plus 1, 1, 1. And it is illustrated here in the Q-sphere. You can also see that. So now we measure either that or that, each with the same probability. Good, so let's try to run that circuit. How do we run it? We have on the very right side here, it says set up and run. So I can choose here, for example, I can start with a simulator, just specify how many shots I want, because I don't want to just have one shot, because if I just get one shot, I might just measure 0, 0, 0. But I actually want to see in a histogram how the distribution looks like, so I know which states I could possibly measure. So I could do that, and then say run on the simulator. But now it tells me this circuit needs at least one measure. Of course, I've created a quantum state, but in the end, what I measure, I'm interested in the classical output, so I still need to add some measurements. Measurements are these things here, which we can just move to measure all the 3 qubits. And I can, again, say set up and run. This time I see here now it's running. And I should very soon get a notification here. Yeah, it's running. I can see here my last jobs. This is now running on the Cousin simulator, so it's running on the cloud. You can either run things locally if you just program them, which is also, of course, nice if you're on a plane and you're coding. You might want to run things locally. But then you can also use the online simulator, the Cousin simulator, where you can simulate more qubits than on your own device usually. Takes quite a while now. Now we see it's completed. And we can here see the outcome, the histogram. We can see out of our 1,024 shots, we got 519 times 111 and 505 times 000, which is to be expected. I mean, the probability was 1/2 and 1/2. The reason we don't have exactly 1/2 is not because we have noise, but it's because, well, it's the same if I tell you to throw a coin 100 times. Most likely you will not get exactly 50 times 0, but maybe 52 times 0 and 48 times 1 or so. But let's do the actually excited stuff and run it on an actual quantum computer. Now we use the simulator, but here you can see I can also choose one of the quantum systems. So I'm having here a bit more devices available than you have. You can see here how many qubits they have, and you can also see the number of pending jobs, or the queue. So what I would do now is actually sort them by the number of jobs. So I can, for example, choose that device, Guadalupe, which only has actually right now 0 jobs in the queue. So if I'm running that now, I should directly be running it. Otherwise, I would first spend some time in the queue, which, depending on the device, might take quite a while. Like actually, if you go on quantum on the dashboard again, on the front page, you have down here, you can see all your systems. And again, for me, it's going to be a few more, because as an IBMer, there's also the private devices that we have available, those that, well, you can buy access to. For you, there's going to be all the free devices. Yeah, loading. Is that the internet connection or the website? And now we can see here the different devices. And we can see the queue, the total number of pending jobs. So for example, for Montreal, there's 450 jobs in the queue. So that's going to take a while if I submit a job there. But then there's some, like Guadalupe, where I send my job. There's a very short queue, and so on. Here you see the open systems are the ones that you should have access to as well. So yeah, let's see if my circuit actually ran. How do I get back here? Wait. Yeah. Jobs. So now I can see, okay, that was the second last one, the simulator. Here's the job on Guadalupe that I just ran. And I can see my histogram. As we can see, now we're not only measuring 0, 0, 0 and 1, 1, 1, but we also measure a lot of states in between. This is now actual noise. Because of course, if I create these gates and I measure them, there's some errors that are induced. Actually, already in the state preparation, there's some errors. Then there's some errors due to the gates. Then there's some errors due to decoherence. And there's some errors due to the measurements. All of that adds to the fact that in the end, we will have some noisy results here. But we can still identify what our state probably was. Another thing you notice is that the probability, the frequency of measuring 1, 1, 1 is smaller than the one of 0, 0, 0. Of course, it could be fluctuations, but actually that is a very common thing. You can see here it's quite a big difference. And that is because the decoherence time plays an important role. And the decoherence time makes our qubits decohering from state 1 to state 0. So that's more likely to happen than to go from 0 to 1. That's why usually on 0, yes?
Just a new question that is not that related. This is run on superconducting.
Yeah, that's superconducting qubits, exactly. Yeah. So yeah, here you can see these are the results. Now, if you want, you can also run your own jobs. For later, I have reserved for the hands-on session, I have reserved some devices, so you should be able, if you use one of the 3 devices that I have reserved, you should be able to directly skip the queue, and your jobs should run first. So yeah, that you don't need to wait for like 200 jobs to be finished ahead of you. One last thing here to show you in the composer is that on the right side, you can actually directly see the code with Qiskit now. You see this is Qiskit code. And it's actually quite straightforward what happened here. So first you have to import quantum register and classical register. Actually, by now we don't, it's fine. It's enough to import quantum circuit usually. You create a circuit by specifying that you have 3 qubits and 3 classical registers. Here they're all combined, but it says C3, which means that there's 3 classical registers to measure out the 3 different outputs. And then I create a circuit that contains them. Actually, I don't even need to specify the registers. I could just say circuit equals quantum circuit 3, 3. Then I say circuit.h, which creates my Hadamard gate on qubit 0. It's enough, again, here to just put 0 rather than the Q register. Then to apply the C0, I just say circuit.cx, and I control it on qubit 0, and the target is qubit 1. I do the same with 1 and 2, and then I do measurements on my 3 qubits. But yeah, so we will see that actually now in more detail in the quantum lab, how we can do more advanced things. Because, of course, this is nice, but that's just to play around with a bit, but we cannot do things like Grover's algorithm by dragging and dropping gates. For that, we need like for loops, if loops, feed in states, and do just more advanced things. That's not what the composer is for. But so what we would actually use for that is if we go to, again, quantum-computing.ibm.com, we can launch the IBM Quantum Lab. And that will open us a Jupyter notebook. And you can then either directly run things online in the Jupyter notebook. So just create a new Qiskit, Python 3 notebook, for example. But then what I would usually do, it already does some imports, is I would run it locally. So you can run it locally if you just install Qiskit and Jupyter notebooks. So what I show you here is how I locally run that thing. But it's the same code. It just, then you need to do installations, and here you can run it directly on the cloud. But of course, if you have like connection issues, that's more annoying. Yeah.
So when you access Jupyter Lab from the IBM site, you are online.
Yeah.
And, but we should do all this stuff offline, to say locally.
As you wish, yeah. So I would usually do things online just because, I don't know, then I have them all, that I don't need the internet connection. I mean, I need it the moment I submit my jobs, but other than that, I don't need it. I have it all like in my own repository on my laptop. I prefer that, but you can also run everything online. It's just, later on we will give you some exercises together with Ticket, so some Qiskit and some Ticket exercises. And I think they created actually an, what is it called? Binder. So I think you can just directly online use Jupyter notebooks. But for example, if I would give you all the notebooks, you would otherwise just need to upload them here, which is also fine. You could just upload the files that I'm giving you here by pressing upload files and then run those. That's also fine, instead of downloading Qiskit, installing it. But the Qiskit installation process and Jupyter Notebooks installation process is also quite simple. Anyway, so let me show you then how the lab works. So, actually Jupyter is nice, you can even do slides with it, with the different cells. I don't know if you're familiar with Jupyter Notebooks. You have these different cells. So I can always add cells and remove cells, and then the cells can be either code, like here, or they can be text, like the other stuff. And then I can prepare it as a presentation. So I'm going to show you 3 different things now that we can do with the Quantum Lab. First, how we create basic quantum circuits and how we visualize them. Then how we run them on real backends. So basically what we did before, but a bit more advanced. And then I will show you the implementation of Grover's algorithm. So we can start by building the first quantum circuit, and we will start by simulating a Bell circuit. So first I need to import from Qiskit, I need to import quantum circuit. I create my circuit as just by specifying quantum circuit 2. So I have 2 qubits. I apply a Hadamard gate on qubit 0, and then a CNOT gate that is controlled on 0, acting on a qubit 1. And I draw it where MPL means that it makes it look a bit nicer. So then we see this is how it looks like. So this colorful gate is from the MPL. Then we now might want to simulate that state. Like we're interested, how does the state vector look of that state? I mean, I guess in this case now we all know what it's supposed to look like. But in general, if you have bigger quantum circuits, of course, if they're too big, we cannot simulate them anymore. But for the smaller ones, those that we can still simulate, we can use the state vector simulator backend. And I'm importing here just something so that I can use LaTeX, that it looks nicer. And I'm importing air. Air is what we use to import our state vector simulator. So I'm having, again, the quantum circuit as before. Actually, this time I just call it QC. They wouldn't need to do it twice, but OK, I forgot about that. So I'm doing, as a backend, I specify that I want to use my simulator now instead of a real backend. This is what I need to specify. So I could just, later on, we will see, I can just replace that backend command by getting an actual device. Then I say backend.run QC, which is my Bell circuit, and then .result. And then I call my state vector psi, and I'm just saying result.give me the state vector, so get state vector, and I plot it with LaTeX. And here we see, actually this time I added an x before, so it's not the Bell state that it has a minus sign here, because we have this x before. Anyway, so you can see this is how I can in general get a state vector from a given quantum circuit. Yes?
So previously you used the QASM simulator, now you're using the state vector simulator?
Yes, exactly. That's different simulator. So the QASM simulator I would use to give me in a lot of shots. So I would use it to just execute the circuit and then I run it with whatever, 1,000 shots or 8,000 shots or 20,000 shots, and then give me the output as results after simulating it, whatever outputs. But then I, of course, have fluctuations and stuff. The state vector is what actually gives me then the state vector, yes. Now we might also want to plot the state that we just computed. For that we have different visualizations. So we have, for example, the Q-sphere that you have seen before in the composer. I just import plot state Q-sphere, and, well, the command is plot state Q-sphere of the state psi. And then we see we have 0, 0, minus 1, 1. Or in that case, we actually have minus 1, 1, plus 0, 0, 0, 0, 1, 1, minus 0, 0, but that's just a global phase. So you can see that you just have a phase of pi between them. Then we can use the so-called plot state city, which where we can see here the real part and the imaginary part. In our case, we only have real numbers, and you can see these correspond to the different matrix entries, basically. So this thing up here is the element of the matrix on the very top left. So 0, 0, ket 0, 0, bra 0, 0. Here the other one that is on the top that has like 0.5 plus 0.5 is 1, 1, ket 1, 1, bra 1, 1. And the ones that are negative are the ones that are ket 0, 0, bra 1, 1, and so on. So if you, maybe actually, just to show you what I mean, never mind. So if I have the state 0, 0, minus 1, 1, then my density matrix is given by 0, 0, minus 1, 1 times, and then again 0, 0, minus ket bra. So we get 0, 0, 0, 0, minus 0, 0, 1, 1, minus 1, 1, 0, 0, plus 1, 1, 1, 1, and of course everything multiplied by 1/2. So that's why these two terms are negative and these two are positive, so we basically just plot the density matrix. Yes?
Can you show the code again where you initialize the state?
Of course. I can also make these available later for the hands-on session, so if you try to work through the exercises, you can access that code. That's what you mean, right? Yeah. So the minus sign here is, of course, is here, but then in the density matrix is at the two corners. That's why we have this plot. And of course, there's no imaginary number, so this is all 0. Let's look at another visualization method, which is state hinten. This is actually the same as before, just with black and white for plus and minus. And I think there's different forms of gray for different values if it's something in between. But OK, this is not so useful, I guess. And here we have the polyvectors. I don't think you have, actually you have seen that in Zoe's talk, I think, that you can write things always by poly operators. So you can write things as like identity times identity plus x times x, and so on. We can always decompose it into a sum of poly operators with different factors before. And so this would be the decomposition into the polyvectors, which is especially useful for quantum simulations and quantum chemistry, these things. Good, so let's see how we can execute the circuit, because so far we just created the circuit, but we have not actually executed it. Again, as when we used the thing before, the composer, we need to add a measurement. So we say circuit.measureAll, and then we draw our circuit. Now we see, now we have the two classical bits here, and the measurements that give us the outputs.
What does initial state equal to that do?
It just means that it tells me here that the initial state is 0. If I can also just leave that.
But isn't it always the case?
Yeah, it's just for the plot. It is always 0, but it just otherwise it wouldn't tell me that it wouldn't plot that 0, because you know that it's 0 if it doesn't say anything else. But I can plot it there just to so you know. Oops. The initialization is always in the 0 base. I mean, I can initialize it in a different state, but that means that I just have the 0 and apply some gates, because physically you always have the 0 state in it. Oh, the measurement, sorry. Yes, the measurement is always in the 0-1 basis. Yes. Oh, now I've added a second measurement. Oh, that's stupid. Okay. That might be complicated now. Let me now run it. I should create that circuit again and, sorry, add just one measurement. So now, as a simulator, we can use the air simulator, which is again different from the custom simulator. It basically does the same, but the custom simulator is what runs online. The air simulator is what runs offline on my computer. So I can choose the air simulator, which will just execute the shots. I say backend.run, the circuit that I specified. Then I want to get the results, which I just get by job.result. And what I'm specifically interested in is to get the number of counts that I have for each state. And those I can then print. So I see we were running the ball state. Basically, we were preparing the ball state and running it. And now I got 474 times 0, 0, and 550 times 1, 1. Again, we have no noise. These are just the statistical fluctuations because we are using the simulator, so no noise yet. A nicer way to plot it, though, is not to just look at the counts this way, but to actually plot them in a histogram. So I can just say plot histogram of my counts, and then we see them plotted in a nice way. And I can just run it again, so you will see it will actually give me different result every time. Yeah. Any questions to the first part on simulators? Otherwise, we would go to running it on the real backend. So for running it on the real backend, the very first time you do it, if you run it online, if you just directly use the notebooks online, you don't need to save your account. But if you do it offline, like I'm doing it in a Jupyter notebook, the very first time that you use it, you need to say ibmq.save account, and you find the token actually in your account. When you create an account, you can find it. It's like a super long bit string that you just need to save once. Once it's saved, you can just say ibmq load account, and then it will always load your account. You can directly access. So usually the hub group and project for, yes?
Yeah, no, you were getting to that. I wanted to ask you if those other three variables were mandatory or...
Yes, so usually for you they would just be the open ones because you have access to the open devices. For me, for example, the hub is the internal one. So I can say hub equals ibmq internal and so on and specify that. For you it would just be the open one. I think it's actually fine if you just give the token and the rest will then automatically be in the open one. But so what you want to do for today is you want to specify the hub to be this one and that group and that project, because this is the one with which you can access the devices that I've reserved for later. The weird thing is it says ETH Zurich IBM here because when I created my IBM Quantum account, I was still affiliated with ETH Zurich. I'm still doing my PhD there, so that's why it says ETH Zurich. They didn't manage to change the name. So anyway, this is how you can get the provider. So this is how you can then access all the devices. It's also, you have with this provider, you will now have access to some of the 7-qubit devices that you would otherwise not have access to. Now we can check which backends we actually have available. So what are the quantum computers, or in general, all backends that we can access, and how many qubits do they have, can they act on? We can see here we have a bunch of different simulators. Don't worry about them too much. We usually just use the cousin one if we want to do stuff online, well, or the state vector if we're interested in getting the state vector. And then here you see the quantum devices that we can access. Lima, Belém, Quito, and those. They have between 5 and 7 qubits. Now what I can choose is, I showed you before where they all have these long queues in general, and you might wait quite a while while being stuck in the queues. So if you don't have a reserved device or something, what you could do is you can say, okay, I'm going to want to choose the least busy device, the one that has the least number of jobs in the queue. And actually, the system is even smart and usually can estimate how long a job takes. Like some jobs take a few seconds, some jobs take a few hours. So it will actually take the one that not only has the fewest number of jobs, but also the shortest ones. And I can specify how many qubits I want. So if I want to have one of the 7-qubit devices, I could say, well, should be more than 7 qubits or something. At least be 7. So if I run that, it will soon. Now it's checking the different queues. Okay, and it shows IBM Q Lima, which is apparently the one that has right now the shortest queue time. Now I can say, okay, job. My job is that I want the backend that I now specified, which is the least busy one, so Lima, to run my circuit. And then I say job.result. But now we get an error message, which is it cannot implement the basis. We have not only used the basis gates. So the problem is that our quantum circuit, the way we specified it, we used, for example, the Hadamard gate. But the Hadamard gate is not something that will be directly implemented by the quantum computer, but it actually needs to be transpiled into different gates that can be done, that the computer does. So what we need to do first is we need to transpile our circuit so that it is specific to our backend and only consists of gates that we can actually directly implement. So if we do that with the circuit we had before, we can see that instead of the Hadamard gate, we now have a rotation around Z, then a square root of X gate, and another rotation around Z. The good thing is these rotations around Z are actually for free in the sense that Z rotations are implemented on IBM by a rotation of the frame, basically. So it's just a computation. It's not actually, they're not applying physically something, but they just rotate the frame, kind of. So you can imagine this is still just one physical gate that is implemented, but we have to do these calculations before and after. And now this can be directly feeded into our circuit. We can also check which qubits we were now using, because when we transpile it, it also chooses in a smart way 2 qubits that have good error rates and that are next to each other usually. So we can see now for the ball state that we prepared, what it shows was that we choose qubits 1 and 2 out of these are the 5 qubits that the device Lima has, and we are now using here 1 and 2. Yes?
What do those lines mean?
These are the connectivities. This is the connectivity. So this is actually very important. We can, in general, like if you look at IBM's devices, I can actually show you some. Let's look at the 127 qubits, for example. The thing is, they are not all-to-all connected. So if I want to make a CNOT gate between qubit 1 and qubit 10, they're usually not directly connected. So I need to first swap the qubits and then can apply a gate. So I can only apply 2 qubit gates between those that are connected. If it would load, well, I can look at it. Here we see it. So we see this is the connectivity map, for example, for the 127 qubit device. So you have to kind of, in a smart way, try to put your qubits such that you have as little gates and swaps as possible.
How does transpile, like, something like that, decide if you have a 2-qubit gate, decide where to put it?
If you have a 2-qubit gate, it will just like check we actually can here see also the error gates. I mean, we can just choose any 2 qubits that are next to each other. And usually, most importantly, if we have short circuits, is the CNOT error, so the error between the 2 qubits. We can see here it's, for example, 1.3%. Here it's 1.9%, and so on. And then there's some that are pretty bad. Okay, this is actually broken. But yeah, so you see they just vary. And then we also have the readout assignment, the measurement error, which is also usually quite substantial. So here it's, for example, oh no, it's actually very small. Okay, 2.4 to the times 10 to the minus 3, but sometimes it's also of the order, here it's 6%. So what it would do, it would choose your 2 qubits that have very little errors, if you anyway only need 2 and that are next to each other. in doing the transpilation. But it goes pretty fast. This is really not a problem. This is always done very fast. Yes?
Are the qubits always physically put in a two-dimensional grid, and then the drawing represents how they are put, or maybe sometimes they are also put in 3D, and the graph is just a representation of the conductivity?
Oh, you mean how they're actually on the chip?
I mean, on the chip of the quantum computer, are the qubits actually in a grid
Oh.
that looks like that, or is that just a...
No, I think this is just the connectivity. I mean, they are probably somehow, probably they're not like exactly like these square kind of things, rectangulars, but like might be, I don't know, they might be round. I actually don't know, I'm not an experimentalist. But the connectivity is like that, and I mean, then also if two qubits are connected, they should be next to each other. And the reason that they're not all connected is that if you have a gate on one qubit and it's close to another qubit, then it might affect the qubit next to it that is connected to it. So if you connect them all, there's much, much, much more noise. So yeah, they figured out that this is, well, apparently a very good layout for at least the systems that IBM uses.
So the qubit swapping that you sometimes need to do,
Yeah.
is that also done automatically by transpilation?
Yes, by transpilation it will also do the swap gates, and it will try to optimize them in a way that you have as least as possible. Yes, exactly.
Can you also check how much qubit operations can you perform before it loses qubits? Or
How much operations you need now?
how many operations can you perform on a single qubit before it loses?
Well, the problem is it's a like continuous thing, right? Like if you do 10 operations, you might still get your right result with 90% probability. If you do 20, you might like it will decohere more and more and more, right? So
Part of the optimization was to perform the less operations as possible.
yes, but then on the other hand, of course, you want to do big calculations. So it's gonna go deeper and deeper, and with error correction and better experimental hardware, yeah, we're trying to optimize these things. So yeah, let's actually see, now that we transpiled our circuit, we can run it on the back end. So we're gonna run the transpiled circuit this time. And we call a thing called Qiskit Job Watcher, which is this nice thing here in the top left corner, which tells me now my job got queued, and it's in queue position 90 and 3. So it's gonna take a while. This is my job ID, which I printed, which is useful if I later on want to access my results again. Like if I want to do other stuff now, I can later on look at that. So because I already assumed that it might take a while to perform this job, I already ran the job before on the IBM Lagos device. And we can now retrieve that job by specifying the job ID from the circuit I did before, and then get the result and the counts, just as we did with the state vector, and then plot them in a histogram. Here you can see how it looks like. You see there is some noise, but it's quite small still. I mean, it's a short, small circuit. Do you have any questions so far? Yes?
If you wanted to force it to be on certain qubits?
You can do that, actually, yes. Yes, I will actually show that in the example that I'm gonna run on Grovos, I think. I think I'm going to show you there. Definitely later in the session that we had, the joint session that we have with Ticket, that's going to be more about error, how to mitigate errors. And there I'm going to show, because that's quite important, because different qubits have different errors, that you specify the qubits that you want to use when you try to characterize your errors that you then later on correct for the same ones. So yes, you can actually just give a layout and say, okay, I want to run it on qubits 1, 5, 8, and then it does that. And then even in the transpilation process, if I give it to that, in the transpilation process, it will still use these 3 qubits and not do any changes, yes?
Yeah, can you specify the number of shots?
Yes, that as well. Sorry, yeah. I actually should have done these things as well. Actually, just here, I can say shots equal to 1,000.
What is the default then?
1,024, I believe. It used to be 1,024. Maybe they've increased it, but... And the maximum amount depends actually on the different devices, what they allow for a maximum number. But you can check it if you, again, go here. You can somewhere see what the maximum amount of shots is. here you see, here for this device it would be 100,000. And I can submit up to 300 circuit in one job. But okay, this is now for the fanciest device, right? But still, yeah.
When you see the plot of the qubits connectivity and the error between them,
Mhm.
is there a way to estimate beforehand, starting from those noises, the error bar of the plots probability that gets out, so that you can estimate if those two bars are different because they are actually different or because of some noise?
Yes. So there is like there's not such a kind of, or I don't know how to do such a kind of error bar, but what you can do is you can simulate a noise model, which is something I will actually also show you in the next session, where we can simulate, like, given all the the measurement errors, the C0 errors, the coherence time of the different qubits, I can apply that to my specific device. I can read in all the information I anyway have. So all the information I have here from the calibration data, I can use that and apply a noise model and then simulate how it would look like. And I can, of course, also in comparison simulate it.
You mean on a local machine so that you have no noise, no real error, you just simulate it?
Well, this I can always do. I can also just like simulate it locally, yes, or on the cloud, but like simulate it without noise. That's what we did in the beginning. I mean, of course, the fluctuations, they depend. It's like a Gaussian curve, right? If this is what you mean, like, of course, if I had no noise, it would still fluctuate a lot. Could fluctuate more or less, but like, yeah. Okay, so I guess I have 15 more minutes, right? We started at 1:45, I think. I'll hurry up. Okay, so now the third part is Grover's algorithm, which you have just seen before. So just as a quick reminder, also so you get familiar with my notation, what I mean by step 1, 2, 3, and so on. Step 1 for me is where I just put all items in superposition, so I just apply a Hadamard gate to all of them. Then I have step 2, which is actually applying my oracle. I think that was basically out of the oracle, that was step 1 in Zoe's thing. And then step 3 for me is what was step 2, 3, and 4 in Zoe's slides, so Hadamard gate, then the reflection around the average amplitude, which is just like an oracle around 0. And then Hadamard again, and then I apply all of these. So steps 2 and 3 I repeat 3 times. In the end I do a measurement. R times, where R depends on the number of elements. So let's not go into too much detail, but I'm just gonna define my phase oracle by specifying the number of qubits that I have, the indices which I want to mark, which is like the winning element, could be multiple, could be 1, and I just call it oracle, so later on in the circuit it will say oracle. So I create a quantum circuit that has n qubits, and it's called oracle. And then I create my oracle matrix, so because later on I will form an operator out of that matrix, by first saying that, okay, it acts as identity on all qubits, because you have seen that it actually, what it does is there's identity on all, but except for a -1, it gives a -1 phase to the to the marked element. So we have a -1 element to the matrix. So this is basically like ket and bra. That's why we have it twice indexed to mark. So the diagonal elements, here we have 1 on all diagonal elements, and now we turn it into -1 for the one that we want to mark. Then we turn this oracle matrix into an operator, so that we can apply to our circuit and return the circuit. And then the fuser is what I just call here all the 3 things together. So Hadamard gate plus this oracle around 0, the UF0 tilde, I think that's also what you called it, and Hadamard again. So we have our quantum circuit again on n qubits. We apply Hadamard on all n qubits just by saying h on rage n. Then this, I'm not sure if she actually showed that, but basically this oracle that we apply in between, here this one, is just like an oracle, but as a marked element it would take 0. So we just can call our function phase oracle with 0 as the marked element, and then we apply another range of n Hadamard gates and return the qubit. Then we put this all together into Grover's algorithm. So we create again a quantum circuit with n qubits and n classical bits. we just determine R, don't worry about that, it's just a formula to determine how many rounds do we need to run in order to reach that, to be optimal. We initialize it with applying Hadamard gates, that's step 1. And then we have step 2 and 3 where we apply our phase oracle and the diffuser, both R times. So here, step 2 and step 3. These both R times, and then in the end we measure and return our circuit. And so let's see how this circuit looks like if we, for example, choose n equal to 5 qubits. Then we can determine that the optimal number of rounds would be 4 rounds. I choose a random element as my marked element, which was now element number 22. And I apply Grover. And here we can see we have the Hadamard gates in the beginning, then our oracle, diffuser, and so on, and measurements in the end. Now we can first see what it's like if we execute that on the simulator. So as before, we get the simulator, we execute it with 10,000 shots, and then plot our histogram. And here we can see this is actually the binary representation of 22, because the element we chose here randomly was 22. And we can see with 99.9% chance we're getting that. The reason we're not getting 100% is not due to noise, but it's because Grover's algorithm is not hitting exactly the top, but we have like the small angle where we're not exactly there. But it's pretty close, so we're doing a pretty good job. Now this, don't worry about that code, I just wanted to show you what happens if we would run. So what I'm basically just doing is running, instead of running optimal R rounds, just see what happens if we run only 1 round. If we run only 1 round, we are going a bit up towards the element that we want to go to, but we're not fully there yet. So you could see if I plotted in a histogram, we could already identify what our element was, but it only has 25% chance of being measured because we didn't apply the whole thing enough times to go all the way up. And if we now would add noise, it would not be that optimal. So here we can see what happens if we apply it once, it's the blue line, twice the pink, 3 times the purple, and 4 times we basically had a 1% chance, the orange, what we did before. So running it optimally 4 times is indeed the best. And now we can actually also run it on our device. We can choose the least busy device. And oh, here's actually what you mentioned before. Here I'm feeding, or what I was feeding when I chose before, I was running it on the Hanoi device, and I was feeding a specific layout. So I wanted it to be run on qubits 1, 2, and 4. Because later on I want to do error correction on those as well. So I would just say initial layout equals, here the layout is specified here. Now we're not doing it because we just choose the least busy device, so I don't know which one it's going to be. It's randomly now marking 2 elements, just to see something else. So now we can see it's 5 and 2 are marked. But again, we probably won't have time. Oh no, that's the one from before, to run our the job. So I did run it earlier as well here on the Hanoi device, as I said. You can tell I need to actually get my internal hub again, because well, the Hanoi device is only part of that one. And you see, this is what we got when we run it on a real device. So there's much more noise, because I did choose the optimal number of rounds. But you can still identify what the 2 elements are that were marked in this case. And now, yes, we still have some time, very good. Because now what I actually want to show you, what I'm more excited about, is rather than showing all this code about constructing Grover's algorithm, I want to show you how it is that actually Grover's is already pre-installed on, there's already a library on Qiskit about it, so you don't need to install all the stuff I just showed you by yourself, but you can actually use directly the library that is there with Qiskit. And what I also wanted to mention is, well, Grover's algorithm, as you saw the way that we defined it, I constructed an oracle and I told the oracle which one is the element that we want to mark. But that's kind of cheating. I mean, then I already know the solution anyway. Why would I even need to run Grover's then? So that's a bit with a similar argument can be done with a phone book. Like if in order to run Grover's algorithm on some phone book, I would need to feed in all the details from the phone book into Grover's algorithm. Feed it all in. But while I'm feeding it all in, I can as well just look for the solution. So what Grover's algorithm is actually more likely, like better applicable for, is so-called satisfiability problems. So that's something where we can actually make use of it, because we don't need to know the solution. It's just running. It's about running some statements and check if they're false or true. And it's statements that are easy to be evaluated, so I can easily evaluate my function, but I might not know what the actual solution is. So let me give you an example. Let's say I want to throw a birthday party, and I have 5 friends: Alice, Bob, Charlie, Dave, and Eve. And I'm wondering, whom of those should I invite to my birthday party? Now I have a bunch of restrictions. One of them is that Alice and Eve are always fighting, so I really don't want to invite both of them. Then Alice and Charlie are actually married, so if I invite one of them, I should invite the other one as well. Then I also really want my party to be a bit cool, so I want to invite at least one of my one of the 3 entertaining friends, one of my 2 entertaining friends, Bob and Dave, so at least one of them I should invite as well. However, I should definitely not invite both of the 3 guys, Bob, Charlie, and Dave, together, because then the party might get out of control. Also, I know that if I invite Bob, he will probably ask Alice about a birthday present. So if I invite Bob, I also need to invite Alice. Not necessarily the other way around, though. And then the last requirement is that I know that Dave will only come if Bob comes as well, but not the other way around. So there's no point in inviting Dave if Bob is not getting invited. So these are now a bunch of restrictions. And I don't know, maybe you've already figured out whom to invite. But the question is, what's the solution? Whom do I invite? Of course, with this, you can maybe figure it out yourself. But if I scale this problem up, it's all statements that I can easily check if they're true or not. You can give me a solution. You can say, what if I invite Alice and Bob? And then I can check true, 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 false, true. Okay, no, one of the requirements is not met. So I can easily check, but it's still hard to find the solution, especially if it's a big problem. So what we can do is we can use rovers for that. And to do so, we need to formulate our problems as a so-called 3-set problem, which, okay, don't worry about that too much. It needs to be in a conjunctive normal form, which is a conjunction of clauses. So each of the clauses, each of the requirements, we need to write as a disjunction. So it's something or something. But let's just look at the examples. The first example was that Alice and Eve are always fighting, so I cannot invite both of them. As a logical statement, that means I cannot invite Alice and Eve. However, this is now not a conjunction of clauses, because a conjunction of clauses would be something or something. But I can rewrite it. This one is actually equivalent to saying not Alice or not Eve. This gives me the same solutions. So this is now fine. And then let's say Alice is person number 1, Bob is person number 2, Charlie 3, and so on. So that statement would correspond to -1, -5. There's always, by default, there's always an or in between. And then there's always a 0 in the end, just for the Qiskit code. So if I want to put all the requirements I told you before, I can put them in this way. So for example, well, Alice and Charlie are married, so I cannot say, not invite Alice and not Charlie. Sorry. One of these 2 things has to be met. Anyway, so, okay, it takes a while maybe to understand that these are the same. I actually gave that as an exercise to my class that I was teaching, and they had quite some fun in trying to figure out the logical statements. But I think at some point you're going to get more used to how to actually phrase some logical statements in this form. Yeah, so if the 0 is just something that you put with Qiskit at the end. I don't know, yeah. Yes?
How can you remove the and in statement 2?
I do not. I just have I can put it as multiple clauses, because it's not, sometimes you cannot put a requirement as one single phrase in that sense, with just one or, and then you can put it as with an and. You can put a conjunction of clauses. And so this is one clause and this is the other clause.
So it's like saying 2.1 A or not C, and 2.2 not A or C.
Yes, exactly. Yes. So in the end, I'm going to have actually 7 clauses. So I just put them as another one here. You can see here I have 1 minus 3 and minus 1, 3. So it's just one more clause. Yes, it's like, exactly. So now I can feed in them into my 3-set problem. It's a bit annoying. I first need to save it and then call it again. And then I can just import from Qiskit algorithms Grover and the amplification problem. And OK, don't worry about the code too much. You can easily find it in the documentation. But basically, I can just run Grover on my, well, after I have here before, whoops, here I have my oracle defined by using this all the logical statements that I encoded in the 3-set file. And now I just run on that the amplification problem on the oracle, and then with Grover I amplify that. And I can see my top measurement is 0, 0, 1, 1, 1. Now what does that mean? We know we had Alice is number 1, Bob is number 2, Charlie number 3, and so on. But with Qiskit it's all the opposite way. So the first one is on the very right side. So that would correspond to invite Alice, invite Bob, invite Charlie. Do not invite Dave, do not invite Eve. And if we want to see how it actually looks like if I simulate it on the device, so here I was just saying top measurement, so it would give me the measurement that has the highest probability. In the histogram, this is what it looked like. And here, this is the 0, 0, 1, 1, 1. So you can check, this is actually the only solution. But yeah, that was just an example. Of course, in this case, you could have done it by yourself, but if we scale it up, that's some way where Grover's algorithm can actually give us a benefit. Now the question is, okay, this was run now on the simulator. What if we would use an actual device? And what I just did here is now I'm transpiling the circuit to see what the depth of the circuit is, so how many time steps would I need. And we can see that it's actually 78, which right now would be too much to give us useful inputs, like 20, 30 is maybe something where we can still get useful results. 78 is too high, but hopefully with error correction, error mitigation, better hardware, soon these problems will be more feasible. Yes. Okay. Now I'm running out of time, so I just very quickly will show the first slide actually of what I wanted to show you about the Qiskit community team, just so you see that as well, because I think now I have to finish, right? So in case you want to learn more about IBM, in general how to use IBM quantum devices and Qiskit, and also more about quantum computing, we have a lot of different options. First of all, if you want to learn more, on qiskit.org/learn, we have the Qiskit textbook with a lot of, it's really like a textbook, so it teaches you all the basics of quantum computing, and then always with code, so that you can directly run the code cells actually online, and directly you just need to evaluate them and see how the stuff you learn in theory can be implemented with Qiskit. Then we have the global summer schools that are online. You can actually also find them all on YouTube, as well as a lot of other videos on YouTube, if you prefer watching videos rather than reading a textbook, for example. And of course, we have the documentation. We have a lot of events with some of, I think not of you, but of the people in the advanced track, actually quite a bunch of them have participated in some of our events already. And then there's things that you can apply for, like if you're teaching, for example, with Qiskit, you can apply to be part of the educators program, which is what I'm now, so that you can reserve your devices. So if you teach with Qiskit, you can reserve devices for specific hours so that your students could all use it. In a similar way, if you have a research project in mind for which you would need to reserve a device, you can also do that. Then you can apply for the researchers program. We have a certification mostly targeted for developers, so they can prove that they have some quantum knowledge. And we have the Qiskit Advocate program, which is nice for people that are just enthusiastic about getting more in touch with IBM researchers. Like you have the chance then to be supervised for a project, and you have just better access to the community in general. So yeah, in case you want to learn more, first of all, we also have the session later on, where we're gonna have hands-on session. So you will get a lot of exercises, small exercises. Actually, it's multiple choice tests, but the idea is that you run code in order to figure out the answer to the multiple choice questions. I will then walk around, and you can always raise your hand if you are stuck, if you have some questions, whatever. That's together with Tqt, so you can then do both the Qiskit and the Tqt questions, whatever is more suitable for you. I think the Qiskit ones are probably more basic, and then Tqt kind of builds on top of that. But also, I will be around for the industry session tonight, and you're always very welcome to just ask me anything. Yeah, and now enjoy lunch. Yes? I will actually upload it, tell the people from Continuum if they can also upload it into their folder. So they created a folder that they will show in our joint session later, where you find all the exercises, Qiskit and Tkit, both of them in a folder. I will ask them to also add the notebook. I will probably not put in the Grover result, the Grover stuff, because it's like self-built stuff, but like all the basic stuff in the beginning, I will put all of that in there, yes.
You mentioned that we can use some sort of connection to be able to use the reserved.
Yes, yes, for that I need your email addresses. I need to add your account. So you need to create an account with your, ideally with the email address that you signed up for, because those I got from Jake. If you use a different one, just tell me your email address so I can add